Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to have you here because, honestly, we're going on a truly fascinating journey today. We interact with heat every single day of our lives, right? When you grab a hot mug of coffee and that heat instantly transfers to your hands, you feel it. When you step out into the freezing winter air and the heat is just sapped right out of your body, you definitely feel that too. But what's actually happening down on a microscopic level? Well, today, we're going to unpack the fundamental science of thermodynamics. We'll look at exactly what heat is, how it moves around, and how we measure it. And then we're going to cap it all off with something spectacular. A look at how a very strange, totally unexpected quirk in physics is literally the only reason aquatic life can survive on our planet. It's a pretty incredible story of science in action.
Okay, let's dive right into this and take a look at our roadmap. First up, heat versus temperature. Second, how heat moves. Third, measuring the heat. And finally, nature's icy magic trick.
Starting things off with Section 1, heat versus temperature, because believe it or not, these are two entirely different concepts.
So to really get this, we need to look at the distinct difference between the total sum and the average. Heat is the total sum of the kinetic energy of all the molecules in a given body. Picture a massive lukewarm swimming pool. Because it's huge, it holds a massive amount of total heat energy. Temperature, however, is just the average kinetic energy possessed by each individual molecule. So think about a tiny little espresso cup of boiling water. It has a wildly higher temperature, a much higher average energy per molecule than the swimming pool, but it contains way less total heat. Basically, heat is the actual energy itself, which we measure in joules, while temperature is the effect of that heat, measured in Kelvin.
Now, to truly understand temperature, we have to look at its ultimate baseline, which is absolute zero. Since temperature is just the measure of molecular movement, what happens if you take all that heat away? Well, you hit absolute zero. Valued at precisely minus 273.15 degrees Celsius, or zero on the Kelvin scale, this is the theoretical point where particles of matter have absolutely minimum motion. The vibration just stops. It's the ultimate zero point of our physical universe, and it gives us a rock-solid foundation for how we scale and understand temperature.
All right, moving right along to Section 2, how heat moves. Because all this energy has to get around somehow, right?
So the crucial point here is that this energy doesn't just jump around randomly. It's transmitted through three specific methods: conduction, convection, and radiation. But regardless of which method is doing the work, there is one unbreakable golden rule governing the flow. Heat always, and I mean always, flows from a higher temperature body to a lower temperature body until they completely equalize. They just want to balance out. When you touch an object and it feels hot, that's just heat actively entering your body from the object. And when it feels cold, that's heat leaving your body and flowing into the object, desperately trying to equalize the temperatures between the two of you.
Which brings us to Section 3, measuring the heat. How do we actually capture these energy shifts in our daily lives?
First up, we have the classic liquid thermometer. You've definitely seen one of these. This device relies purely on the physical expansion of a liquid, usually mercury or some colored alcohol. Remember earlier when we talked about how heating an object makes its molecules vibrate and push apart? Well, a liquid thermometer uses that exact same principle. When the bulb at the bottom comes into contact with something hot, heat transfers into the liquid inside. That liquid gains energy, its overall volume increases, and it's physically forced to expand forward up through that incredibly narrow capillary tube. Wherever the liquid finally stops expanding, boom, that gives us a highly accurate temperature reading.
But let's see how this concept builds into modern technology with the digital thermometer. Instead of relying on a physically expanding liquid, this device uses a tiny, hypersensitive component called a thermistor, which is connected to an internal electric circuit. When the tip of this thermometer touches a hot object, the actual electrical resistance of that thermistor changes based on the heat it absorbs. The circuit instantly measures this incredibly precise change in electric current and translates it into the digital number you see popping up on the screen. It is literally taking thermal energy and translating it into an electrical signal.
And then we have this amazing piece of tech, the radiation thermometer. Unlike the first two we looked at, this one doesn't even need to touch the object. Its working principle is based entirely on capturing the intensity of infrared radiation produced by a body. You point the sensor, a lens inside focuses on the target, and it captures the invisible infrared radiation coming off of it. The heat carried by those signals generates electrical currents, instantly giving you a contactless temperature reading. It's wildly fast, and it's a perfect real-world example of capturing heat as radiation, which, if you remember, was one of the three movement methods we just talked about.
Okay, buckle up, because we are entering our final section. Section 4, nature's icy magic trick.
I want you to consider this scenario for a second, especially if you live in a colder climate where you've probably seen this firsthand. In the dead of winter, a local pond completely freezes over, right? It turns into a solid sheet of ice on top, and the outside environment drops well below 0 degrees Celsius. So how exactly do the fish and all the other aquatic life survive in the water underneath? Why doesn't the pond just freeze completely solid all the way down to the muddy bottom, trapping and freezing everything inside? Well, the answer lies in a genuinely bizarre physical anomaly.
And this brilliantly illustrates what scientists call the anomalous expansion of water. Now, normally, as any liquid cools down, its molecules lose energy, they pack closer together, the volume decreases, and it becomes denser and denser until it finally freezes solid. But water? Water completely breaks this rule. When water is cooled down and hits 4 degrees Celsius, something strange happens. It hits its absolute maximum density and its absolute minimum volume right at 4 degrees. If you cool it down even further towards 0, it actually starts expanding again. It disobeys the normal expectations of thermodynamics right at this crucial little window. And because of this strange anomaly, a literal lifesaver of an event happens in that winter pond. As the freezing winter air cools the pond water, the water eventually reaches exactly 4 degrees Celsius. At this precise temperature, remember, the water is at its absolute heaviest. So what does it do? It immediately sinks straight down to the bottom. As the surface water continues to get colder, dropping to 3 degrees, 2 degrees, 1 degree, and finally 0, it actually becomes lighter than the 4-degree water sitting below it. So it stays right on top. And when that 0-degree surface water finally turns into ice, it floats. It forms this perfect protective floating icy roof over the entire pond, perfectly insulating the heavier 4-degree liquid water resting securely at the bottom for the fish.
In fact, our source text sums this up perfectly. As the surface water reaches 0 degrees C, it freezes and floats on the surface of the water below. Therefore, fish and other aquatic animals can survive in the water below the ice. The heaviest water, that perfectly habitable 4-degree water, is safeguarded at the bottom. Without this specific anomaly, where water bizarrely becomes less dense as it approaches freezing, the coldest water would just continually sink. The lake would freeze completely solid from the bottom up, creating one massive deadly block of ice.
Which really leaves us with this incredible, mind-bending thought to close out on. If water simply followed the standard, everyday rules of thermodynamics like almost everything else in the universe, if it just contracted continuously until it froze solid from the bottom up, our world's aquatic ecosystems would be completely wiped out every single winter. Would life as we know it even exist? Probably not. It is such a perfect reminder that these seemingly dry rules of physics, the total kinetic energy of heat, the specific movement of molecules, these strange little anomalies of density, they are literally the very mechanisms writing the rules for life on Earth. Anyway, thank you so much for joining me on this explainer today as we dove into the fascinating science of heat. Keep questioning, keep observing, and I'll catch you all next time.